Well, welcome back to part 2 of our lesson on continuous functions. And as I begin this lesson, I look out the window, I see the snow is coming down pretty good, so it was certainly a good idea to cancel classes for the day. All right, well, let's start with some laws of continuity. So let's suppose that f and g are continuous at x equals c, then the following functions are continuous at x equals c. The function f plus g, and let's write that f plus g or f minus g. The sum or difference of two continuous functions is itself a continuous function. Let's call this 2, and let's say k is a constant here. So the constant times a continuous function is a continuous function. K is a constant. The product function f times g would be continuous at x equals c if both f and g are continuous at c. The quotient function, f over g, is continuous at x equals c if f and g are continuous at x equals c. And, of course, we have to stipulate that g of c cannot be 0. All right. Well, we have a continuity law that involves composite functions as well. I need some board space here. Maybe I could sneak it in over here. Let's call this 5. So if g is continuous at x equals c, and f is continuous at g of c, then f of g of x is continuous at x equals c. And we have a law that involves inverses as well. So if f is continuous on an interval I, with range R, then the inverse function, f inverse, is continuous with domain R. Okay, so with these laws in mind, we're able to list a bunch of functions that are continuous on their domains. Let's take a look at these. The following functions are continuous on their domains. Your polynomials. So polynomials are real nice functions that are continuous everywhere. It's continuous on their domains. The domain of every polynomial is all reals. So if I use one of the laws that we just had up there a moment ago, the one that said if f and g were continuous at c, then f over g is continuous at x equals c, then I can say that rational functions are continuous on their domains. let's see, your power functions. Right, functions of this form, where this p is a real number. Your power functions are continuous on there. Your exponential functions. And these guys, f of x equals a b to the x. Sine, cosine, tangent, secant, cosecant, and cotan are continuous functions on their domain. So let's write the trigonometric functions. Trigonometric functions. Sine x, cosine x, tan x, and then the reciprocals. Cosecant x, secant x, cotan x. Those functions are continuous on their domains. And then if I use the law of continuity that talked about inverses being continuous, then the logarithmic functions are continuous. Logarithmic functions are continuous because they're the inverse of the exponentials. And then let's just say the inverse trig functions. Inverse trigonometric functions. Okay. So here's a list of families of functions that are continuous on their domains. All right, well, let's do an example here. Get rid of this. You'll see questions in the Achieve homework or the written homework where you're given a piecewise function and asked to discuss the continuity. So let me put one up here. Let's discuss the continuity of this piecewise function. And it's defined like this. X plus 1 for x less than 1. And how about 1 over x for x greater than or equal to 1. So discuss the continuity. Tell me where this thing, does it have any discontinuities? Okay, so note that this piecewise function is made up of a polynomial and a rational function. So both of those functions are continuous on their entire domains. So if you've got a piecewise function that's made up of continuous functions, then the only place that you might have discontinuities would be at these any of the switching points. Like there's only one up here, x equal 1. So I have to examine what happens at x equal 1. So let's see. The function has this function will be continuous at x equal 1 if those three conditions are satisfied. If the function's defined, so let's see, f of 1, well, the input is 1, so I'm on this branch. Right, so f of 1 would be equal to 1 over 1. F of 1 is 1. Then I got to think about the limit. Does the limit exist? Well, that two-sided limit, this two-sided limit will exist if the one-sided limits exist and are equal, so we better look at those. Let's come in from the right first. All right, I want to know what happens or what these function values look like as we let x get closer and closer to 1 coming in from the right. So for values of x that are greater than 1. So if x is greater than 1, that tells me I'm down here on this branch. So as x gets closer and closer to 1, these function values start to look more and more like 1. 1 over 1. Come in from the left. So as I let x approach 1 coming in from the left, values of x that are less than 1 Well, that tells me I'm up here on this branch. And so as x gets closer and closer to 1, this function f starts to look more and more like something close to 1 plus 1. So it starts to look more and more like 2. All right, well, the one-sided limits both exist but are not equal, so this limit does not exist. There's a discontinuity. There's a discontinuity at x equal 1. This function f is continuous everywhere except at 1. Right? And in fact, we know what kind of discontinuity it is. Right? It's that one where both the one-sided limits exist and are not equal to one another. So it's got a jump discontinuity there. In fact, let's graph it. Let's see it. All right, let's graph this thing. So for values of x that are less than 1, the function is this linear function, x plus 1. So it's a positive sloped and has y-intercept 1. And so it would look like this. Let me open circle there. All right. There's x plus 1 for x less than 1. And then when x is greater than or equal to 1, the function looks like 1 over x. So when it's at 1, when x equals 1, the function value is 1. And then it looks like 1 over x there on out. So there's the graph of that piecewise function. And yeah, I can see it's continuous everywhere, except at this place right here where the graph has a break in it, we've got a jump discontinuity. All right. Well, one more thing that we can look at here. In our last class, a couple classes ago, we investigated limits. Right? And we investigated them by looking at graphs or tables of values. So knowing that a function is continuous, I can figure out the limit by just substitution. Because if the function's continuous, then the limit there is equal to the function value. So I could just evaluate the function at that point to get the limit. So let's do that. Let's investigate some limits and see if we can't use continuity to help us. So let's look at this one. The limit as x approaches 3 of x plus 2 all over x squared plus 2x. Okay, so the function that I have up here is a rational function, and I know all rational functions are continuous on their domains. So the question then becomes is 3 in the domain of this function? Well, yeah, 3 would be in the domain of this function because if x is equal to 3, this denominator's not 0. So this rational function is continuous at x equals 3, therefore this limit equals f of 3, where f is this function. So that limit is equal to that 5 over, what is this, 9 plus 6, 9 plus 6, 15. So 1/3. All right, so I didn't have to set up a table of values and let x approach 3 from either side, getting closer and closer, and seeing is this function approaching some finite real number. Had I done that, I would have seen that, yeah, it's getting closer and closer to 0.33333333. Okay, couple more. How about this one? We'll call that one 1, this one 2, and this limit as x approaches pi of 1 over cosine x. Okay. All right, well, here, the function that I'm looking at, I could think of it as the constant function 1 divided by the cosine function. And this constant function is continuous everywhere. And this function is continuous on its domain. So the quotient of those two would be continuous everywhere except if this denominator is equal to 0. Okay, so this constant function is continuous at pi. Cosine is continuous at pi. This quotient function is continuous at pi because cosine pi is not equal to 0. So that continuity law says that this quotient is continuous at pi. Therefore, this limit is equal to the function value at pi. This is 1 over cosine pi. And so that's what, 1 over negative 1. That's negative 1. One more. The limit as x goes to 3 of 10 raised to the x squared minus 2x power. Okay, let me think of this function here as the composition of these two functions. Let's let f be the exponential function 10 to the x, and g be the function x squared minus 2x. And so that 10 raised to the x squared minus 2x, isn't it this? It's f of g of x. Right? Drop this function into that function, I get 10 raised to the x squared minus 2x. Okay, so we did have a continuity law that said if this function g was continuous at c, and this function f is continuous at g of c, then the composition is continuous at c. So both of these functions are continuous on their domains. Both of their domains are all reals. So this composition here will be continuous everywhere as well. So since this function is continuous at 3, that limit there equals the function value at 3. So to evaluate the limit, I just need to substitute in 3. So this limit is 10 raised to the 3 squared minus 2 times 3 power